So here I am on 16th of March 2023, Thursday, 5:03 p.m. at Nicer Bhubaneswar. Bhagirathi Hostel, 127 room. So I'm here to understand the theory of condensed matter theory. I haven't been able to follow what sir is doing, both due to my personal interests and the teaching methods. But I'm as usual. I'm always interested to do my self-study and understand it as much as possible. I'm averted to look into books like Ashcroft and Moon, Kittle, and all those stuff, mainly because they're physics textbooks, and it just gives me no hope in terms of mathematics I aspire. But the lecture notes by David Tong are perhaps a beautiful source for people like me interested in mathematics and physics. So yeah, these are what I read now, what I explain to myself now are basically the notes of David Tong, solid state physics. I'm not going to do the first chapter. That will be far away from my academic course structure. So I've started chapter 2, band structures. I've completed it in a reasonable level, but I would like to read it again. There are many holes to fill up. There are many gaps to fill up. Some calculations I wish to do, some pretty naughty physics stuff. It's going to be not that much satisfying like mathematics, but it should sure satisfy me in the sense that I am understanding it in some level and trying to complete it in some level, right? Yeah, I'm establishing the ground that this is not going to give me much satisfaction, but this is the way I would like to take things. This is the way I would like to read things. This is what I like, and I'm just doing it. It just gives me more energy this way. Ironically, this also takes a lot of energy. But yeah, what doesn't? What doesn't if you want to do things good? What doesn't take more energy, So here I am redoing band structures, chapter 2, solid state physics, lecture notes by David Tong. Let me check if I'm recording my voice. I am. Interesting. Band structure. This chapter will start a journey in the world of condensed matter physics as a study of properties of stuff. Our interest lies in a particular and familiar kind of stuff, solids. So we focus on solids in this course as solids. So it's a collection of tightly bound atoms for most solids. These atoms arrange themselves in regular patterns on an underlying crystalline lattice. Some of the electrons of the atom then relocate, dissociate themselves from their parent atom and wander through the lattice environment. The properties of these electrons determine many of the properties of solid, not least its ability to conduct electricity. So these solids form so-called lattice. Most of the solids form so-called a crystalline lattice. A crystalline lattice that underlying another the structure, right? And there are some electrons which so-called wander around the wandering things. They wander. We'll explain kind of. Some electrons which wander around, and these explain the properties of solids. One might imagine that the electrons in solid move fairly in a random fashion as they bounce from one lattice site to another like a ball in a pinball machine. However, as well, this is not at all the case. The more fluid nature of quantum particles allows them to glide through a regular pattern, almost unimpeded, with a distorted energy spectrum, the only memory of underlying lattice. So again, as he says, the electrons, you might expect them to move in a random fashion, but turns out it's not so random after all, but they kind of move unimpeded from one lattice site to another, unimpeded, with a distorted energy spectrum. The energy spectrum is distorted. In what sense? We will see. But in one sense that they are moving unimpeded. Yeah. And this distorted energy spectrum, and as claimed by Tong, is the only memory of the underlying lattice. If you remove this lattice, you just expect it to be a free particle. If you add the lattice, you get a distorted energy spectrum. That's the idea. So the main idea, even when I read it last time, is that there is this lattice. You add electrons to it. You try to explain this model, right? You try to write a good Hamiltonian explaining these things, this periodicity in things. You try to explain what is the Hilbert space of this Hamiltonian, what are these energy states, that is, and you see many subtle things, many straightforward things, many fermionic things. So we would like to do that. Basically, we would go as far as possible writing Hamiltonians, explaining spectrums, understanding the properties of solids by that spectrum, what it means, that you get the bands, you get sort of band structures and stuff. That's the whole point of this chapter, is to explain band structure, right? In some sense we do. Band structure are easy. You just try to write a Hamiltonian where an electron can hop into one of the neighboring sites, and you write a Hamiltonian first in a one-dimensional model. You try to understand what it implies. You get a tight binding picture, nearly free electrons, tight binding picture. You get some states, you get a band gap. You see that the band gap starts from at the end of the Brillouin zone, right? At the end of Brillouin zone. What is a Brillouin zone? Brillouin zone is like the momentum region where your perturbation is essentially non-degenerate, in the sense that the degeneracy which existed simply doesn't split, right? Simply doesn't split. Simply doesn't split. That means that okay. Yeah, simply doesn't split. That's the idea, and these calculations are what from the basic the this, these calculations are important. You are analyzing it. You're just not see. One thing is to actually know how do we realize band structures. Is that through this? We know that right now. You have the big picture in your minds, in my mind, but the calculations are what makes a theoretical physicist skillful, capable of doing it. He can this allows that tools of exploring things. This chapter will give me that ability to explain solids using lattice, what I can do with it, how can I introduce potentials, how can I introduce electrons, how can I just see the system theoretically, right? So that's the aim of this, right? And it is interesting, right? Even if I'm interested in mathematics, and no matter how many approximations physicists use, I should be able to explain that system in whatever capacity I can. I'm interested in that system. I am interested in that system. Uh, hmm. The fact that I'm interested to explain that system in a more rigorous way is another issue, but I want to explain that system, and this chapter allows me to gives me the tools to explain that phenomena, that natural thing. That whole physics is that way, right? But when I am learning, I would like to see the rigor in things, right? Rigor in things, right? Now this makes me feel like, oh man, I'm not interested. I mean, am I interested in pure mathematics? And what is it even? That's what I feel right now. But math is beautiful. I mean, that suits me a lot, right? You see, making the subtle abstract things, theory out of such abstract little things is very interesting. If you don't do that, you kind of get dissatisfied by that, so yeah. So what I'm trying to understand physics. That's the problem. I guess I should see it as I think I should see it as I should see it as some subject which helps me see nature. It gives me the tools to understand nature. It doesn't claim precision. It doesn't claim anything. It gives me tools to do it. Successful tools to do it. That's it. It gives me successful tools to do it. Right? So yeah, keeping that in mind, right, and letting things open. I don't know what will happen for my interests. My interest in mathematics may change. I don't know, but as of now, it's really beautiful. It's really good. I wish there was more exposure to mathematical physics here. Yeah. And the sad part of this timing now is that a volleyball match is going on outside. I don't know, between some Centurion University or GCP or whatever, Katak University. They're playing good, pretty tough bastards who practiced volleyball good. Anyway, so that's what this is about, and that's what he said. That's what Tong said in the first intro to the chapter. In this chapter, we will focus on understanding how the energy of electron depends upon its momentum when it is in a lattice environment. The usual formula for kinetic energy is one of the first things we learn in theoretical physics as children. As we will see, a lattice changes this in interesting ways. The consequences, which we'll explore in chapter 3. So chapter 3 is what I aim to reach now, right? Understanding chapter 2 properly and completing the chapter 3 is my aim, right? So the usual formula for kinetic energy E, half mv square p square by 2m, is one of the first things we learn in theoretical physics as children. As we will see, a lattice changes this in interesting ways, the consequences of which we will explore in chapter 3. Lattice changes this in interesting ways, the consequences of which we will explore in chapter 3. Okay. I don't remember. I don't get what is referring to by the usual formula for kinetic energy being changed by the lattice. What does lattice do? What does the energy by the lattice? What did you see? It's basically the same thing, but there is a correction term given by the magnitude of potential, right? And there is also non-degenerate perturbation term, which Tong claimed very haphazardly to be small, big. What the hell, man? I don't get it. I wish I can solve that thing. It's very delicate. If you get that wrong, it's and still you're trying to be pretentious. That's just bad. Of course, that might be correct. I just need to figure out properly. I didn't figure it out last time. I wish to do it this time. So yeah. So yes, energy changes this in interesting ways. Interesting ways. We didn't see the consequences. Yeah, we just saw the band gap. I mean, that's the basic of everything. So we will explore in chapter 3. Interesting. I'll get to the 1D model now. Introduction done. 1D electronic model. We begin with some particularly simple toy models which capture much of the relevant physics. These toy models describe an electron moving in one-dimensional lattice. We'll take what lessons we can from this before moving on to more realistic descriptions of electrons moving in higher dimensions. So we'll take as many lessons as we can, starting with tight binding model. Also, this is a long process. I'm afraid of one thing. My roommate is going to come in now, and I won't have this freedom to talk. So that's a bummer. And I respect that this takes a long time, right? I am motivated to do it, but I'm not facilitated to do it. I thought I could go to computer lab, but that's tricky. There's so much noise there than this. It is silence in some sense, but it's a constant background and stuff. I think I can go there after he comes. Yep. Tight binding model, 1D dimension, will take as many things as you can, but they will start with tight binding model. Is a caricature of electron motion in solid. Okay. Tight bending model is a caricature of electron motion in solid in which space is made discrete. The electron can sit only on the location of atoms in the solid and has some small probability to hop into neighboring site due to quantum tunneling. Okay, a lot of things. One, it's just a toy model. It's just a caricature of electron motion in a solid. So we make solid discrete. First step, we make it discrete. We put some electrons in. Electrons can sit only on the location of atoms in the solid and has some small probability to have. So the electrons can only sit here, or here. And once it is here, it can hop here and here with some probability. Okay, to start with, a solid consists of one-dimensional atom. Solid consists of one-dimensional lattice of atoms. This is described by n points arranged along a line. So yeah, we'll begin with taking n points. N points along the line. N atoms. This is described by n points arranged along a line, each separated by distance a. Distance a. Consider a single electron moving on this atom. We'll assume that the electrons can only sit on given lattice point. It's not allowed to roam between lattice points. But we'll assume that electrons can only sit on a given lattice point. It's not allowed to roam between lattice points. Oh. What? Wait, what? It's not allowed to roam between lattice points? Really? Acha. Between lattice points. Okay. So the first thing is electrons on lattice points. There's no flexibility. Oh man, there is no flexibility. It's an asterisk. Second thing. Okay, well, let's see the implications of the first thing. Consider a single electron moving on this lattice. We'll assume that the electrons can only sit on a given lattice point. It's not allowed to roam between lattice points. Okay, this is supposed to mimic the idea that electrons are bonded to atoms in a lattice. Okay, why is this happening here? Why is reasonable choice? Is because electron on lattice points okay, there are lattice points. Why this makes sense? This kind of mimics the fact that electrons are bounded to atoms in a lattice. Okay, the wandering thing. Okay, now this kind of contradicts the fact that the wandering, like, why do you wander? Okay, well, the remark is that you cannot wander. You wander atom to atom, not between them. Right? So that's the thing. That's a very hard-bound rule for me to digest it, but we'll we'll see. I don't know. We'll see what we're neglecting in approximation later. So this is why it got its name. Tight binding approximation. I don't know. He's saying the distance is less or whatnot. But yeah, the approximation will be described later. To be described. Yeah, so the problem is that there are many loopholes left. There are many non-definitive things left in the theory. That's what makes it, but it is tough, right? Physics, life is tough, so they just try to. It's a personal taste. It has become a personal taste of human being to do physics in this way. You may not do physics in this way. Physics started out to be this way, right? It gave you big, beautiful platforms, whatever that is. Knowledge, scientific knowledge, scientific methodology. Physics gave you a nice little scientific methodology to explore your things, explore your interests in matter, physical things, But then mathematics came and it stirred the world, and as it is, I feel like it's stirring physics too. Mathematics is stirring physics too. It's time that physics incorporates mathematics and writes its way. I don't expect everyone to do it, but I wish I can do it. It's what my interests are, as I see right now. But anyway, the electron sits on the nth atom. We denote the quantum state as n. Okay, and basically this is straightforward. This is just label. Okay, these guys are considered orthogonal to each other. Okay, this is also good. I mean, one thing is you give me a Hamiltonian, and the other thing is you start from backward, right? Starting backward. And reasonably, it's back and forth. That's what physics is, right? A back and forth between between experiments, between experiment or reality and the formalism, right? You construct, but in order to construct a formalism, or in order to construct a formalism, you see it, you carefully incorporate things of reality into it, and so in the end you get a little beautiful theory. You get happy by seeing what God explains, because you slowly try to incorporate them and incorporate not all little things. You didn't incorporate band structure in this. You only incorporated the fact that you happen to had this very little things like lattice points tightly bounded. This is interesting. I mean, this is approximate things and explain reality. That's very interesting. It works, why not? Good, fair enough. Clear the total Hilbert space as n has dimension n and is spanned by n, with n equals 1, 2, 3, so 1 to n. So the Hilbert space is essentially all the states. It's essentially this. It's a span of this. Right? It's a span of this, an n-dimensional Hilbert space. Okay, now what the superposition means physically is that there's probability of this in this state, but when you measure it collapses to a point, right? That's the thing. You collapse to a point. Well, that's the thing. With leaking in this. Okay, you literally have a Hilbert space in front of you. What do we want from this next? Is energy basically. Uh-huh. You might need energy of these states, right? You can label them always. Maybe not, no, not always, and not until you know some things. Okay, we are feeding this into the theory. Okay, feed some things into the theory, feeding some reality into theory, things into the theory, feeding some things into the theory. So Hilbert space is 1, 2, 3, so on to n, span, dimensional. Okay, now the next thing we would like to feed in is something related to energy, I suppose. Yeah. What kind of Hamiltonian will govern the dynamics of this electron? Now we are here to. Okay, this is Hilbert space. This is the Hilbert space. Hilbert space. What we need is a Hamiltonian. A Hamiltonian governing the system. Simple. Hamiltonian, what kind of Hamiltonian will govern this dynamics of this electron? If the electron just remains on a given atom, an appropriate Hamiltonian would be, okay, it's just sitting on an electron, it's just sitting on that. What it is, it's just this, right? It's just this, basically. It's just this, in the sense that H naught M is equals to E naught E naught. That's it, right? Not M. A static picture. Electron on a given atom M. Yeah, each of the positive states, each of the position states N is an energy eigenstate of H naught with energy E naught. The electrons gone by this Hamiltonian don't move. This Hamiltonian is called boring. Anyway, to make things more interesting, we need to include the possibility that the electrons can tunnel from one side to another. So he says tunnel. One state to another state. Tunnel. Really? It should tunnel? What exactly is quantum tunneling? I mean, what I remember is, when is quantum potential? Yeah, exactly. There's a potential barrier, but yet it can penetrate through it. Okay, even if there's a barrier, it can penetrate through it. We explicitly saw this in quantum mechanics 1, which I don't remember explicitly the calculation. So that's the essential crux. There's a barrier between them which breaks. Okay. So yeah. So to make it more interesting, the Hamiltonian we need to include the possibility that the electrons can tunnel from one side to another. How to do this? Well, the Hamiltonian governs time evolution. Yes, In some small time increment of time delta t, a state evolves as minus I delta t by h bar Hamiltonian psi plus everything of order delta t square. Yeah, this is an infinitesimal transformation, and I wish I could have excuse me. I wish I could have actually, understood this more structurally in the course, right? Like the way of how Chetan sir teaches us, right? Actually, or mathematically, wish I understood it. But yeah, we were little kids back then. We didn't know much. What can I expect? Right? You're not genius. You are a little guy who tries to work hard, try to understand things. Anyway, this means that if you want the possibility for the electron to hop from one side to another, you should include in the Hamiltonian a term of form Mn, which takes an electron at site n and moves toward an electron at site m. So what we want is, if you write around, we don't need just an m. Right? Wow. Wait. What do you need my Hamiltonian? Have you got Hamiltonian? Will come on the time evolution. Acha, that's interesting. You see. Oh, I see. What? Yep. He didn't write this just for fun, right? Of course, he didn't write just for fun. Okay. What he is implying here is the wave function is evolved by this term called h psi. So if your function psi is it was an m, but it is also an m, but maybe it is also going to some n, right? And it finally rains. Wow. I have to go. I will write this Hamiltonian and I am going without solving the tight binding model. So, you see, h psi depends on n. How could you add that such term? This motivates our final form of the Hamiltonian. H equals to E naught n minus, okay, wait, what? Okay, we should include in Hamiltonian a term of form Mn, which takes an electron at site n and moves toward electron at site m. Okay, there is no partial movement here, right? If you want to go from m to n, you straight up give a term called minus m and plus n, right? So if you apply this h psi h on some some linear combination of m. Okay, let's just study this Hamiltonian. Okay, you really beat around the bush if you don't. It is probably not practical to pray in rain, huh? Anyway, so this feels steady. Let's study the Hamiltonian. Okay, you can never derive it. You cannot derive things in physics. You can only, by intuitively, you can add them. Okay, deriving them from the first principles is really up to mathematicians. Okay. So the point is, what is this? It's clearly m minus t n. So what happens here is n plus. Okay, let's write it carefully. So this term is done. Okay, so what happens is this cancels out if you just subtract with the psi, right? And what happens to this term? It is delta n plus 1 m summation n plus 1 is equals to m. N is equals to m minus 1. When m is n minus 1, this happens. So it is basically this, a probability of this much on that side plus a probability of it is also equally probable to now this is given by the time evaluation operator. It's not just it's gone, doesn't cancel out. It's a factor. There's a factor multiplied to it into I by h bar delta t and stuff. Okay, so this then it becomes t times that is n plus 1. N is equals to m plus 1 basically. So interesting, right? A probability to enter in that state, and it to remain in that state also, right? Which is basically E naught minus I delta t by h bar, delta m bar to hm is equals to psi t, psi prime, where psi was just t, time evolution with given by h cap. So that's that. You have introduced successfully these things. That's what we wanted. The coefficient t is absorbed here, right? So yeah, so our final Hamiltonian reads E naught n minus t summation n plus 1 plus n plus 1 n. Okay, This is connecting itself. This is connecting to the next atom. This connects to the previous atom. N to n plus 1 and n plus 1 to n. Okay. 3 different terms. Okay. So first a comment on the notation. The parameter tree is called the hopping parameter. Hopping parameter. I'm a little distracted by the fact that it's raining outside in summer for the first time. It's really good thing to go out and have some fun, but I have 3 pairs to do and I don't know what the hell, right? It is not time. It is simply a number which determines the probability that a particle hop to neighboring side. Okay. Ratio t square by e naught square will determine the probability. Okay. Yep. Well. T square by e naught square will determine the probability, really. Probability of what? So we'll hop into a neighboring site. That is if you just m plus 1 se block karega. It is at m, right? And if you just do it at m and this is m plus 1, m plus 1, m minus 1, you should be able to do that. I mean, I just did. Sure. What? Wait, what? This and well, just if you just calculate, then this gives you the probability of hopping into that and this, but you should somehow, well, it's Hermitian operator. H dagger H is 1. Really? It's Hermitian. Okay, it's a really good opportunity to see it actually. This is where, stuff. This is interesting stuff, you see, but am I really motivated physically to calculate this and check it? H dagger is basically H again. Right? H dagger is H, really? That's the Hermitian definition, right? Fuck's sake. So what's H inverse? What the hell? What the hell? Unitary operation? Oh no. Okay, rip. Okay. Okay, well, that sucks. H inverse H. I don't know how to construct H, but I don't know how. Like Tong said, it's just T naught square by E naught square because are orthogonal states, I guess. But I don't know. It's something that should be left it as a homework problem. Probability of hopping to n or n plus 1. Okay. Now back to the physics encoded in H. We have chosen a Hamiltonian that only includes hopping terms between neighboring sides. This is the simplest choice. We will describe a more general choices later. Okay. One dimension. This is the general choice. Moreover, the probability of hopping to the left is same as the probability of hopping to the right. Hopping probability left, right. Hopping probability left, right are same. Okay, this is required because H must be an admission operator. H must be a mission. So this must happen. Okay. If you just take, that these will be the same, then it's really good. There's one final issue. We have to address before solving the spectrum mesh. What happens at the edges? Again, there are a number of different possibilities, but none of the choices affect the physics that we're interested in. Choice is to declare that the lattice is periodic. Declare lattice is periodic. So the Hilbert space is not just n plus 1 dimensional. This one, it's right of n, which is identified as again 1. So whatever I blabbered about Hilbert space is not just that or something. That's simply not true. Okay. I want to eat some good food though, man. I think I'll go to the Biggie Burger and get a burger. Yep. Okay, so that's the thing. We have set up some ground rules. Declare lattice is periodic. What about the edge cages, right? Okay, I mean, it just starts with that and this, and that's interesting. Okay, n plus 1 equals to n. I mean, the state is equal, not just 1, 2, 3, not just, no. So, the next step is to solve the tight binding model. So you kind of move on with things like you're not deriving the Hamiltonian. There's no point in that. But how much you understand the Hamiltonian is what's important, right? So what do I understand about that Hamiltonian? It's that it is a Hermitian. So you kind of fix that both the probability of moving left and right is equal, because you need a form of n plus 1 and n. That exterior product of n plus 1 and n. Okay, you need that. Why do you need that? Without that term, you won't be able to include a non-intrinsic atom. You need to go to the next atoms. So you are required by, again, the time evolution operator requires h psi into itself, and if you really want to go to the next neighboring site, you got to include this term, because when you apply it, you saw that there is some probability of going to t minus 1 and plus 1, and tada, that's the simplest way to include it. Again, this is just saying you cannot prove everything precisely. When I say that, This is the simplest. I don't have a way to prove it. Mathematically, I mean. Physically, you just say that it is, you can rule out one by one. The careful analysis is not possible here, and that's what I'm interested in usually, and that's where things are bad. See, Sajak asked me example of things, and this is just way of doing it, right? The theory doesn't facilitate for letting analysis in this, you know. Of course, I agree that this is for many reasons. It's not even required, probably, right? But just imagine this. घर का तपेलेंट याद आ रहा है यार. Fucking hell. This weather, that hot onion-filled tupperland. Too good. Anyway, so that's the thing. How much you understand? One thing, it's how much I understand about the Hamiltonian. It should be Hermitian, so the parameters are same. Helping parameter is kind of same for both. This comes from the facts that you need the exterior product between two different states. Otherwise, you will fail. You will fail to include the left hopping and right hopping, which you can see that by applying it on M, and you get this term. So that's how I reasonably understand it. Now, the more understanding more of this term requires someone to guide me, right? To give me some homeworks problem, just like Chetan sir does in his course, right? That's what we need. So what I will do now is go to Tong's website and see if he has some good problems or whatever they are. Problem set 1, scattering, really? What? Okay, Bundy van structure. Variational methods, really? Okay, 5A. Things were started from 5A. Flockey matrix. Oh my god, this is 1D band structure and he's already going too deep. Interesting. Also, there are very less people who care about this formalism stuff, right? Like Ravi sir, he just pushes on and stuff, to understand that formalism, giving more homeworks about it, only Chetan sir does, Science ma'am does. They are real formalism people. Anyway, I should close this session for now as part 1 of this endeavor and restudying the condensed matter theory. Yep, from David Tong notes. Alright, meet you soon. It's 6:03 p.m. right now. It's exactly 1 hour before I started. Yep, exactly 1 hour since I've started. And I'll have a biggie burger. I'll enjoy some weather. I'll have that smell of soil, wet soil. and I'll come back only to start it again.